Summer 1939. Tempelhof Airport, Berlin. Paul Pleiss inspected the custom-built chassis one final time before departure. The vehicle was ready for the journey 11,000 miles across 11 borders, Berlin to Calcutta. His German colleague, an engineer finishing work at the same manufacturing firm, had agreed to share the adventure. As they prepared to depart, the German engineer raised a practical concern. Emergency water. The route crossed regions where supply would be uncertain. He knew where to find a solution. At Tempelhof, the Wehrmacht maintained a stockpile of fuel containers, thousands of them, staged in preparation for mobilization. The engineer had access. He selected 3, mounted them beneath the chassis, and secured them with straps. No authorization was requested. No paperwork was filed. The containers were marked Wehrmacht Einheitskanister, standard military issue, developed under strict secrecy since 1937. Pleiss examined them with professional interest. Each container held 20 litres. The construction was unusual. 2 stamped steel halves, welded together, painted feldgrau. 3 handles allowed flexible carrying positions. A cam lever closure required no tools to open. The design appeared deliberately engineered, far more sophisticated than the fuel cans Pleiss had seen in the United States. They crossed the first border on June 12th. Then the second, third, fourth. The containers performed exactly as intended. No leaks, no failures. By the time they reached India, Pleiss understood he was carrying something significant. Then the order came. Goering dispatched a military aircraft to retrieve the German engineer. The recall was immediate. Before boarding the plane, the engineer handed Pleiss a folder complete manufacturing specifications for the containers. Dimensions, materials, welding procedures, interior lining composition. Everything needed to replicate the design. Pleiss continued alone to Calcutta, stored the vehicle, and flew back to Philadelphia in August 1939. Europe was weeks from war. He met with U.S. military officials and described what he had seen. The German containers were superior to anything in the American inventory. The specifications were complete. The design could be copied immediately. The officials listened politely. Without a physical sample, they explained, no action could be taken. Pleiss was instructed to wait. The vehicle remained in Calcutta for 10 months. Extracting the containers alone risked customs, seizures, and diplomatic complications. Pleiss arranged to ship the entire car routed through Turkey, around the Cape of Good Hope, arriving in New York Harbor in the summer of 1940. By then, the Blitzkrieg had swept through Poland and France. German panzer divisions had moved fast, supplied in part by the very containers Pleiss was trying to introduce to the American military. He sent 1 jerrycan to Washington immediately. The War Department examined it and made a decision. The United States would retain its existing design, a 10-gallon cylindrical can left over from World War I. It required 2 screw closures, a wrench to open, and a funnel to pour. The design was approved for continued production. The single German container was forwarded to Camp Holabird, Maryland, for technical evaluation. The report would be dated September 18, 1940. It would be titled, Advantages of the German Can. The specifications remained in Pleiss's folder, complete, unimplemented. The jerrycan arrived at Camp Holabird, Maryland, in late summer of 1940. Engineers from the Ordnance Department's Vehicle Testing Division were assigned to evaluate it. They measured, weighed, and documented every feature. The assessment was thorough. 3 handles positioned to allow 1 man to carry 2 full cans or 4 empty ones. A cam lever closure secured with a gasket, no tools required, completely leak-proof. Cross-indented sides that strengthened the structure while allowing for thermal expansion. An air-breathing tube from the spout to an air pocket beneath the handles, enabling smooth pouring without a funnel. Most significantly, a recessed welded seam that joined 2 stamped steel halves, protecting the joint from impact damage. The interior revealed additional sophistication. A plastic coating lined the steel, a technology adapted from beer barrel manufacturing. This lining prevented corrosion and allowed the container to hold either fuel or water without contamination between uses. On September 18, 1940, the evaluation report was filed. The title read, "Advantages of the German can." The document listed every superior feature. The conclusion recommended immediate adoption. The War Department made a different decision. The German design would be modified for American production. The size, shape, and three-handle configuration would be retained. Everything else would be changed. The recessed welded seam was replaced with rolled seams, crimped joints around the bottom and one side. The reasoning was documented. Existing manufacturing equipment could produce rolled seams faster, and vast quantities of this machinery were already in American factories. The plastic lining was eliminated. Fuel cans would use bare steel interiors. The cam lever closure was replaced with a screw cap, identical to the fittings used on World War I containers. Warehouses held millions of these caps in storage, already paid for. A petroleum engineer attached a note to the production order. He wrote that storing gasoline in containers with rolled seams was unsafe. The seams would be prone to failure under stress. The note was dated October 1940. Production authorization was issued November 1940. The modification was complete. The advantages had been removed. The German method was precise. Two halves of stamped steel were pressed into shape, each forming a mirror image of the other. The halves interlocked at the center line and were welded together in a single continuous seam that ran around the container's perimeter, identical to the construction method used for automobile fuel tanks. The weld was recessed, set approximately 3 millimeters below the surface of the steel. This protected the joint from impact damage during handling and transport. When containers were stacked or dropped, the welded seam remained intact. The interior received a coating of impervious plastic, a material originally developed for lining steel beer barrels. The coating was applied through a dip process that ensured uniform coverage across all internal surfaces. This lining served two critical functions. First, it prevented corrosion of the steel, extending the container's service life. Second, it created a barrier that allowed the same container to hold fuel on one occasion and water on another without cross-contamination between uses. The closure mechanism used a cam lever system. Pressing down on the lever created pressure against a rubber gasket, forming an airtight seal that required no additional tools to achieve. An air-breathing tube ran from the spout opening down to an air pocket positioned beneath the handles. When the container was tipped for pouring, air flowed in through this tube, preventing vacuum formation and enabling smooth, continuous flow without the need for a separate funnel or vent. The external surface featured cross-shaped indentations pressed into both sides during the stamping process. These indentations served dual purposes. They stiffened the container walls against deformation, and they provided expansion space when temperature changes caused the contents to increase in volume. The three-handle configuration allowed a single soldier to carry two full containers simultaneously, one in each hand using the center handles. Alternatively, 4 empty containers could be managed at once by gripping the outer handles of adjacent pairs. Capacity was standardized at 20 liters. Weight when empty was 11.5 pounds. Weight when filled with gasoline was approximately 45 pounds. The American redesign retained the external dimensions and the three-handle arrangement. Everything else was modified. The two-piece welded construction was replaced with a three-piece assembly. A bottom panel was stamped separately, then joined to the body using rolled seams, metal edges folded over each other and crimped together under pressure. One vertical seam and one horizontal seam encircled the base. These seams were not welded. They were not recessed. The crimped joints remained exposed on the container's surface, vulnerable to stress and impact. The plastic lining was eliminated entirely. The interior remained bare steel, untreated. This saved manufacturing cost but meant the containers could not safely alternate between fuel and water. Residual gasoline would contaminate any water subsequently stored. Corrosion became inevitable. The cam lever closure was replaced with a screw cap, identical to those used on World War I-era containers. Opening required a wrench. The air-breathing tube was omitted. pouring required a separate funnel to prevent spillage and allow air entry. 2 additional tools were now necessary for basic operation. The weight decreased slightly, 10 pounds empty versus 11.5 for the German version. This represented the only measurable advantage of the American design. The capacity remained 20 litres. For comparison, the British container, known universally as the flimsy, used an even simpler construction. Multiple flat panels of thin tin plate were joined with crimped or soldered seams. The corners, where 3 seams intersected, represented the weakest points. During transport across rough terrain, these seams frequently split. Capacity was 18 litres. The single handle was a bent strip of steel, uncomfortable to grip and inadequate for prolonged carrying. When used in North Africa, the flimsy demonstrated a loss rate between 20 and 50% of contents during a typical journey from depot to frontline units. The structural difference was fundamental. The German container used one protected weld. The American version used multiple exposed crimps. The British design used many vulnerable seams. Under field conditions, one method held fuel. The others lost it. September 1942, Cairo, Egypt. 2 weeks before the Battle of El Alamein, 2 American quality control officers, recently posted to refineries in the Middle East, sent a cable to Washington. The subject line read, "Fuel container losses." The message stated that 40% of all gasoline shipped to Egypt was being lost through spillage and evaporation before reaching forward units. The 40% figure was an estimate, deliberately high to provoke response. It worked. Washington cabled back immediately, requesting verification. The officers arranged inspections at fuel depots behind Montgomery's lines. The conditions they found were worse than anticipated. Fuel arrived by rail from ports in 55-gallon drums with rolled seams and friction-sealed caps. Local labourers handled the drums roughly. Many leaked before being transferred to smaller containers. The next link in the supply chain was the 5-gallon petrol tin, the flimsy. These square containers, made from thin tin plate with crimped seams, had been used for decades to transport lamp kerosene. They were never designed for gasoline in combat conditions. In the desert heat, the tins swelled and burst at the seams. Spillage during pouring was constant because funnels were required and often unavailable. One quartermaster submitted a detailed report. 70,000 gallons had departed the coastal depot by rail. 30,000 gallons arrived at forward positions. 40,000 gallons, 57%, had been lost in transit. His superior officer noted that this was considered a good effort compared to other supply runs. British General Auchinleck later provided his assessment. He estimated that 30% of all petrol was lost between base and consumer. He added that the overall loss was incalculable when measured in tactical terms: tanks immobilized for lack of fuel at critical moments, aircraft grounded, pursuits abandoned, ships and merchant seamen lost while transporting replacement fuel that would itself leak away before reaching the front. The British historian Desmond Young documented it after the war. No one who did not serve in the desert can realize to what extent the difference between complete and partial success rested on the simplest item of our equipment and the worst. In contrast, when Allied forces captured German supply dumps, they prioritized taking the jerrycans above almost any other equipment. British soldiers used captured German containers in preference to their own whenever possible. The Long-Range Desert Group, after the recapture of Benghazi in late 1941, was able to equip entire units with captured jerrycans. The production statistics told their own story. By May 1945, the European theatre of operations required 19 million jerrycans to support American forces. Monthly replacement demand was calculated at 1.3 million, not for expansion, but simply to replace containers that were lost, damaged, or had disappeared. In October 1944 alone, 3.5 million jerrycans were reported missing. The numbers accumulated. The seams continued to fail. The fuel continued to leak. The pattern repeated across 3 years of desert warfare. In 1940, General Wavell's forces defeated the Italian 10th Army in North Africa decisively and pushed west toward Tripoli, But within days the fuel ran out, not because supply ships failed to arrive or depots were empty, but because the containers had leaked during transport. Vehicles sat immobilized, and the advance stopped while the Italians regrouped. In 1941, General Auchinleck launched Operation Crusader and defeated Rommel's Afrika Korps, driving the German forces into retreat, but the pursuing tanks exhausted their fuel within days as containers failed again. Rommel's forces withdrew intact, reformed, and counterattacked 6 months later. In 1942, General Montgomery prepared for El Alamein with careful fuel calculations. But this time his supply officers had something different. Thousands of German jerrycans captured after the recapture of Benghazi. These were issued to forward units before the battle began on October 23rd. The fuel supply remained consistent throughout the campaign. The pursuit continued without interruption, and Rommel was pushed back across Libya into Tunisia. The containers held. August 1944 brought a different kind of failure. Allied forces broke through German lines in Normandy and advanced rapidly, while thousands of tons of fuel sat stockpiled in rear depots. Trucks were available to transport it forward, but the containers were not. 3.5 million had been lost or abandoned by October. Forward units requested fuel, the depots had it, but there was nothing to move it in that would not leak. The advance stalled not for lack of fuel, but for lack of containers. The variable in each case was the container design. The flimsy failed, the rolled seam American design leaked, the German welded jerrycan held. Victories that should have been decisive became incomplete. Pursuits that could have ended campaigns became pauses. The fuel existed, but the means to deliver it did not. The detail was structural, and the consequence was strategic. The German recessed welded seam was protected below the surface and sealed completely. The American rolled seam was crimped at the edges and exposed to stress. One method held fuel without loss. The other leaked under field conditions. The modification was documented September 18, 1940. Production began November 1940. By May 1945, 19 million were needed. The detail was identified, the detail was removed, the cans leaked. One seam, two methods. The difference.